Hello everybody, it's Tarun. Welcome to your 10th tutorial in the signal system and control course. In the last tutorial we ended the unit 3, which was Fourier series representation. And in this tutorial I'll start with unit 4, which is continuous time Fourier transforms. So now let's start. The Fourier transform is frequency domain analysis of a signal. And in the Fourier series representation we talked about periodic signals. But whenever we extend Fourier series to a periodic signal, then it becomes Fourier transform. And it is the basic foundation of frequency domain analysis methods for continuous time signals. So now let's see what we'll cover in this unit. So the first thing is what is Fourier transform for aperiodic signals. Second thing which I'll teach you is Fourier transform for periodic signals. Third thing is properties related with continuous time Fourier transforms, or I'll use CTFT as the abbreviation. The next thing is the convolution property and multiplication property, which is a part of properties, but I'm going to teach them separately to you because they are important ones. And the last thing is frequency response and the differential equations related with the Fourier transform. So now let's get started. So what is Fourier transform? It is a frequency domain representation of aperiodic signals, and to do this what we are trying to think aperiodic signals as periodic signals with infinite period. So now let's see with an example. Here you can see that this is a aperiodic signal, square wave xt, where xt equals to 0 for mod t greater than t1. So if I take this periodic square wave x cap t or x alternate t, where omega naught is equal to 2 pi by t, and it is a periodic square wave, then we can observe that if capital T tends to infinity, then x cap t will be equals to x of t. So this is something how we are going to understand aperiodic signals. We are considering the aperiodic signals as infinite periodic signals. So now let's see the Fourier's representation of this periodic signal. In the frequency domain, if I try to find out the Fourier series coefficients of x cap t, then you can find that the Fourier series representation of a square wave is sinc function. So this is something of the form of sinc function. And I have rewritten it in this form, that I have taken t here, tak equals to 2 sin omega t1 upon omega, and I have replaced k omega naught with omega. And I have assigned it to x of j omega. So x of j omega is called the Fourier transform of this signal. I'll just go to that thing, how to find the Fourier transform, but just to understand here, I have represented it with the x of j omega. So you can plot the graph of this function x of j omega, and you can see that for different values of t, you will get different envelopes. So these are the envelopes, the curves. Let me just show you. So this is one envelope, and for t is equal to 4 t1, it has 3 values inside it. For t is equal to 8 t1, it has 6 values inside it. And for moving forward, you can see that the values inside the envelope increases when I increase the time period. So it shows that tak will go to x of j omega as t tends to infinity. So this was what I was trying to tell you. So now let's see it more general way. So I have taken TAK, which is x of j omega. Okay, and I have I have not taken TAK. I am trying to find out AK, which is this thing, and 1 upon T, that T has been taken here. Okay, so when I try to solve it, I have replaced the limits with the minus infinity and infinity, and k omega naught with omega, then it will be x of j omega. Okay, so x cap t is sigma k equals to minus infinity to infinity ak e to the power j k omega naught t, and which is equals to 1 upon 2 pi summation k is equal to minus infinity to infinity x of j k omega naught e to the power j k omega naught t into omega naught. So here you can see that as t tends to infinity, x cap t tends to xt. So now let's see what is Fourier transform. To find out the function, the Fourier transform function of any signal, you need to integrate it over minus infinity to infinity, and then the function multiplied with e to the power minus j omega t dt. Okay, so and it is represented by this notation, x of j omega or anything of j omega, and you can also find the inverse Fourier transform. Okay, it will be useful when you are given the Fourier transform of a signal and you need to find the original signal. So to find out the original signal, xt will be 1 upon 2 pi integration minus infinity to infinity x of j omega e to the power j omega t d omega. So there are two things to keep in mind whenever you are using Fourier transforms, that in the Fourier transform we are multiplying e to the power minus j omega t, and it is integrated with respect to dt. Okay, and in inverse Fourier transform we are multiplying e to the power j omega t. Okay, here it is positive, in Fourier transform it was negative, and the integration is done with respect to d omega. Okay, these two things you must keep in mind to not get errors when you are solving the problems related to it. Okay, and now let's see the shorthand notation for this. Xt double-sided arrow, and over the arrow we write f for Fourier transform, and it is Fourier transform signal. Okay, or x of j omega equals to f and curly braces x of t, and for inverse x of t equals to f inverse x of j omega. Okay, so now let's see the convergence of the Fourier transform. We are given x of j omega is equal to this thing. Okay, and we are trying to find out that x cap t is equal to 1 upon 2 pi minus infinity to infinity integral x of j omega e to the power j omega t d omega is a valid representation of x of t. So similar to Fourier series representation, there are two conditions and forms of convergence of the Fourier integral. First one is finite energy condition, which is similar to the mean square error term. Okay, which was there in Fourier series. So the signal xt must have finite energy. Okay, this is the expression for that. Okay, and the Fourier transform x of j omega is finite, and energy of x cap t and xt is 0. Okay, these are the finite energy conditions for Fourier transform. Okay, and now the second condition for convergence is Dirichlet conditions. Okay, these are the same Dirichlet conditions which was there in Fourier series. The first one is the signal xt must be absolutely integrable. Okay, but there it was over one time period, and now here it is in the minus infinity to infinity zone. Okay, the second property is that the property or Dirichlet condition is that xt must have finite number of maxima and minima within any finite interval. Okay, and it should have finite number of discontinuities within any finite interval, and there is one more condition in this which was not there in Fourier series. It is that these discontinuities must be finite and fulfilled. Okay, and then x cap t will be equals to x of t. And the similar condition for discontinuities which were there in Fourier series is that x cap td is equal to x of td plus x of td minus upon 2. Okay, the function x cap t will not be equal to x of t at these discontinuities. And there is remark related to it, which is that the above conditions, okay, the convergence conditions guarantee that the Fourier transform exists. Okay, and however there are some signals which do not follow these conditions but still have Fourier transform. Okay, and one important example of that type of signals is periodic signals. So now let's see first some examples. Okay, we are given a signal x of t equals to e to the power minus at ut. Okay, ut is the unit step function for continuous time. Okay, and real part of a is greater than 0. So if I am trying to find out x of j omega, which is Fourier transform, okay, it will be integration minus infinity to infinity x of t e to the power minus j omega t dt. Okay, since we are using u of t, it will be integrated only from 0 to infinity. So the limit is 0 to infinity e to the power minus at, and it multiplied with e to the power minus j omega t dt. Solving the integral, you will get this minus 1 upon a plus j omega e to the power minus a plus j omega t in limit 0 to infinity, which will be 1 upon a plus j omega. Okay, so now let's see the second example, which is unit impulse. X of t equals to delta t. Okay, and x of j omega will be minus infinity to infinity x of t e to the power minus j omega t dt. Since you know that x of delta of t will be valid for t equals to 0, so this integral will be 1. Okay, so the Fourier transform of delta t is 1. So this is the graph of delta signal, unit impulse signal, and it is the graph of Fourier transform of the delta signal. Okay, the third example is shifted unit impulse. Here x of t is equal to delta t minus t naught. Okay, so if I am trying to find out x of j omega, which is Fourier transform, I'll try to find out integration minus infinity to infinity delta of t minus t naught e to the power minus j omega t dt. Okay, if I will solve this, I will get e to the power minus j omega t outside, which is constant, and the remaining term will be 1 because delta will be valid for t equals to 0 only. So the Fourier transform of delta t minus t naught is e to the power minus j omega t naught. Okay, so this is the curve of delta t minus t naught, and it is the magnitude spectra of the Fourier transform, and it is the phase spectrum. Okay, so the fourth signal, which is rectangular pulse signal. Okay, in this signal I'll let you know more about the sinc function. Okay, so the signal is defined like this: xt is rectangular t by capital T1. Okay, it is equal to 1 when mod t is less than T1 by 2, and it is 0 for mod t greater than T1 by 2. So if I am trying to find out x of j omega, since the signal is valid from minus T1 by 2 to T1 by 2, we will integrate it over there only. Okay, and the value is 1, so the integration value inside it will remain only minus e to the power minus j omega t. Okay, so if I integrate it and put the values, I'll get this function. Okay, sine function, because I'll get something like e to the power minus j omega t, e to the power j omega t minus e to the power minus j omega t upon 2j, something like that. So I can write it in the sine function. Okay, now I have multiplied t1 by 2 both sides, so I'll get t1 sine omega t1 by 2 upon omega t1 by 2. Okay, which is t1 sinc omega t1 upon 2 pi. Okay, here if you want to add pi, you can add, or if you don't want to add pi, then you can also do this problem without using the pi inside it. Okay, so this is the Fourier transform of rectangular function. So this is the original function R, and this is the plot of sinc function. Okay, So there is some remarks related with these. In the above problem we use two frequently used functions. Okay, the first one is rectangular pulse of length tr. Okay, and the unit amplitude, so which was the rectangular function, and the second function which we used was sinc function, which was sin pi t upon pi t or sin t upon sin t. Okay, here you can also use sin t upon t. So there are some properties related to the sinc, that sinc of 0 is 0. Okay, so you might be thinking that sin 0 upon 0, how it is 0. In the earlier calculus you might have learned that when limit tends to 0, sin of x upon x is 1. Okay, and integration minus infinity to infinity sinc of t is 1, and integration minus infinity to infinity mod sinc is infinity. Okay, so now let's see the second topic in this unit, which is Fourier transform for periodic signal, which next tutorial. So thank you guys for watching. I'll see you in the next tutorial.